Okay, now that we've finished our hyperbolic content, we're going to look at two questions which are going to draw on a variety of different parts of the hyperbolics chapter. So example number 1. Here we have a hyperbolic curve. The region R is bounded by the x-axis, the y-axis, the line x equals a, and the curve y equals cosh of x. Given that the y value of the curve, y equals cosh x, is 13/5 when a is positive, that's this point here, we're going to find the value of a. Okay, that's the first part. Second part, find the equation of the normal line to the curve at the point a 13/5. So we're going to find the equation of that normal line, and then we're going to find where that intersects the x-axis. And finally, we're going to rotate that region around the x-axis, and we're going to find the volume of revolution. Okay, so let's start at part I. Given the y value of the curve, y equals cosh x, find the x value at that point. Okay, so from the formula book, we have a definition for the inverse cosh function. So we know that cosh of this thing, cosh of a, is 13/5. So we can use that to say that a must equal the inverse cosh, which is the r cosh function, of 13/5. Now from the formula book, r cosh is going to be the natural log of that, so 13/5, plus the square root of 13/5 squared, subtract 1. Okay, so that is given in the formula book, obviously with an x in there. So r cosh of x is log x plus the square root of x squared minus 1. So that's in the formula book. I'm using x is 13/5 in this case, and I can evaluate that. So that's going to be the natural log of 13/5 plus 169 25ths minus 25 25ths square rooted. 169 minus 25 is 144, and that square roots nicely to give 12. So I'm going to have 13/5 plus the 12/5. And that is the natural log of 25/5, which is going to be log 5. So my value of a, therefore, is log 5. Okay, that's that one there, log 5. All right, part 2. We're going to find the equation of the normal to this curve at the point here, at the point when x is log 5. All right, so the equation of the normal is something that was studied right back at A-level mathematics. We're going to need to differentiate and then find the negative reciprocal of that gradient. So for part 2, we're going to differentiate the curve. So we've got y equals cosh of x. So that means y primed is sine of x. And we want y primed at the point of when x is log 5. So we want sine of log 5. Okay, so on the calculator, we can go into math. We can go to option, sorry. We can go to hyperbolic functions, and we want the sine of the natural log, which is that button there, of 5, and that will give 2.4. You could run it through the exponential definition for sine, that's fine. In fact, some cases you would have to do that if it showed detailed reasoning, but in this case, we can just pop it in our calculator to obtain that is 2.4. Okay, so that's the gradient. Therefore, the gradient of my normal is going to be the negative reciprocal of that, because it's normal, it's perpendicular. So that is going to be minus 5/12. Okay. All right, so we've got the gradient, and we know that it goes through the point log 5, 13/5. So we're going to use these two pieces of information to find the equation of our normal. So y minus y1 equals n times x minus x1. And then, of course, we can tidy that up to say y is going to be the natural log of 5 times x sorry, that's minus 5/12. Start again. Minus 5/12 times x. And I'm going to get plus 5 log 5 on 12. And I'm going to get plus 13 on 5. And that's the equation of my normal at that point. Okay. And then part 3. Oh, no, sorry. And then I need to find where this normal intersects the x-axis. Okay, so to find where this is going to intersect the x-axis, I'm going to set y to 0. Because that will be where this intersects the x-axis. And I will get that x is going to equal, bring that across to this side, and then times by 12, I'm going to get 5 times log 5 plus 13 times 5. 13 times 12, which is 156. Where's that side? Okay, that's still on 5. And then I need to divide by 5, so that's going to be divided by 25. Log 5 plus 156 25ths. So the point that it intersects at is log 5 plus 156 25ths, 0. Okay, that's my coordinate of where that's going to cross the x-axis. All right, and then part 3. That region is now rotated 360 degrees around the x-axis, and we're going to find the exact volume of revolution. So just to recall the volumes of revolution, the formula for it around the x-axis is equal to pi times the integral between our two x limits of y squared dx. Okay, so that's the formula you need to know to find the volume of revolution around the x-axis. So in this case, y is cosh of x, and the x values are 0 and log 5. So the volume around the x-axis is going to equal pi times the integral between 0 and log 5 of cosh squared of x dx. Okay. Now, if this was a cos, we would be expected to use a trigonometric identity at this point, but it's not, it's a cosh. You could use a hyperbolic identity, but it's not expected. You're expected to move into exponential form for this. So that's going to be pi times the integral from 0 to log 5 of cosh squared, which is going to be e to the 2x plus 2 plus e to the minus 2x, all divided by 4. So that's using the exponential definition of cosh and squaring it. And then that's going to be with respect to x. And then I can integrate each of those terms, just using A-level maths methods. So that's going to come down as a divisor. So I'm going to get an 1/8 e to the 2x. That's a half, so I'm going to get plus a half x. And then I'm going to get minus an 1/8 e to the minus 2x. And that's evaluated between 0 and log 5. Okay. All right, run those through and we'll get 6 terms. So we're going to get pi into an 1/8 e to the 2 log 5. That's the same as e to the log 5 squared. That comes in as a power. And then e to the log will cancel. So that's just going to be 25. And that's going to be plus a half log 5. And then I'm going to get minus an 1/8 times, and then this time the minus 2 will come in as a power. So it's going to be log of a 25th. And then e to the log will cancel. So that's times a 25th. And then plugging in 0, I'm going to get minus an 1/8 minus 0. And then minus an 1/8. Okay, so those are my terms. Those actually all cancel with each other anyway. Well, so 0 and these two cancel. So I can tidy these up. And then I can leave it as my exact form. The question does say exact, so I must leave it as an exact answer. So I've got an 1/8 times 25, it's the first number there. And I've also got minus an 1/8 times a 25th. So minus an 1/8 times a 25th. And that's 78 25ths. So that's my number. And then I've also got this log 5 there So I'm just going to leave that as a half log 5. You could pull a 50th out of the bracket so that there's no fractions in the bracket, but that answer is fine. It's exact. Okay. What we should do is just check that that is a correct answer. So what we can do is we can integrate our function, which was y squared, cosh. So I'm going to write that as cosh of x squared. I'm going to evaluate that between 0 and the natural log of 5. I'm going to times that number by pi, and that gives me that. And what I should find is if I plug this into the calculator, I should get the same decimal. So pi times 78/25 plus a half log 5. There we go. Okay, so that confirms that all of my working here is correct. And I can move on to the next question without worry. Okay, question number 2. All right. Prove using the exponential definitions for sine and cosh that sine of 2t is 2 sine t cosh t. Okay, so there are lots of hyperbolic identities. You don't need to know any of them. The only one that you can just state is in the formula booklet, which is cosh squared minus sine squared is 1. However, you do need to be able to prove them on request using the exponential definitions. So this is the one we're going to prove this time. I'm going to move from right to left, so I'm going to use the exponential definitions for sine and cosh, and then we're going to plug them into the right-hand side, and we're going to arrive at the left-hand side. Okay, so 2 times sine of t times the cosine of t. So that is equal to e to the t minus e to the minus t over 2. And then I'm going to times that by cosh, which is e to the t plus e to the minus t over 2. Okay, I have separated them with dots, but just to make it a little bit clearer, I'm actually going to put them in brackets. Just so there's no uncertainty as to what I mean. Okay, I can multiply out the bracket at the top. I'm going to leave the 2 there for now. So it's going to be e to the t times e to the t is e to the 2t. Then I've got e to the t times e to the minus t is plus 1. Then I've got minus e to the minus t times e to the t is minus 1. And I've got minus e to the minus t times e to the minus t, which is minus e to the minus 2t. And the 2 times 2, that's still in the bottom. I've not done anything with that. So that remains as a 4. Okay. The plus 1 and minus 1 cancel, and I can cancel the 2 and the 4 down to make just a 2 in the denominator. So that's e to the 2t minus e to the minus 2t, all divided by 2. And that is, by definition, sine of 2t. Okay, so we've proven that this identity is true. Part 2. A curve C has parametric definition, x equals sine 2t and y equals 2 cosh t. And we're going to find the Cartesian equation for the curve, stating any restrictions on x and or y. So what we've got here is x is defined in terms of parameter, y in terms of the parameter, and we're told the parameter is any real number. Okay. We need to eliminate the parameter from these 2 equations. Now the way we're going to do that is we are going to, like we would with a trig case, we're going to use some kind of hyperbolic identity, which you're given in the question. Maybe the one above as well. So we're told that x is equal to sine of 2t, which we know, even if you couldn't do part I, is 2 times sine t times cosh t. And we also know that y is equal to 2 cosh of t. Okay, so it's quite easy to replace the cosh with a y on 2, we can see that. But then we've got this sine kicking around, not quite so simple to get rid of. But what I'm going to do is I'm going to take this and I'm going to square it to give me x squared equals 4 sine squared t cosh squared t. And then I can use an identity here, which is in the formula booklet, which is cosh squared minus sine squared is 1. So that means that sine squared is exactly the same as cosh squared minus 1. And then I've got my cosh. And now I can see that I've got cosh appearing twice and no shine. So I can use this definition in here. So that's going to give me that x squared is equal to 4 into cosh squared of t, which is y on 2 squared, subtract 1, times cosh squared of t again. Okay, tidy that up. I can bring the 4 into the bracket. It's going to cancel with the denominator here and make that a 4. So it's going to be a y squared minus 4. And then I can multiply out that bracket and I get y squared. And then I've got a 4 in the denominator. That's it. Okay, so x squared is this thing. But to get from here to here, I squared the expression. I've got to be really careful. Sorry, the equation. I've got to be really careful when squaring. So I'm going to introduce what's called phantom solutions, which are solutions that aren't on the original curve. In this case, I'm just going to condition it that y must be greater than 0. And the reason I can justify that is if I go back to the definition of the curve, y is 2 cosh t, which means y must be positive, because cosh is never negative for real input t. So since cosh is greater than 0, I'm going to say that y must be greater than equal to 0. In fact, it could be a bit more specific than that. Cosh is greater than equal to 1, so therefore y is greater than equal to 2, because I've got 2 times cosh. So therefore, y must be greater than equal to 2. And that's my condition, which the question asked for. All right, third and final part of the second example goes a bit like this. We've got a point, general point xt, yt on the curve C. We're going to find in terms of t the equation of the tangent to the curve at that point. Leave your answer in the form y equals ax plus b, where a and b are functions of t. This is going to be essentially a parametric form of the tangent, and as you vary t, you move up and down the line, and the tangent will go with it. Okay. So, part 3, we're going to need to find the gradient. So, we call back to A-level mathematics, which obviously further mathematics can do. We know that dy by dx is going to be equal to dy by dt divided by dx by dt, by the chain rule, essentially. Now, dy by dt is going to be 2 times sine of t, and dx by dt is going to be 2 times cosh of 2t. Okay, you need to know how to differentiate these. Sine differentiates to cosh, cosh differentiates to sine, so it's nice and easy. And the 2 will then come out as a multiplier, which is why I've got an extra 2 in this denominator. The 2's will cancel, so that is going to be sine of t divided by cosh of 2t. That's the gradient in terms of t. Okay. So I've got the gradient. It's a tangent, so that is the gradient. I'm looking at the coordinate xt, yt, so that's going to be sine of 2t and then 2 cosh t. And what they've done is they've actually, in the question, they've replaced this lowercase t, the parameter, with a capital T for the equation, for the parameter value at a general point. So I'm going to replace the lowercase t's with capital T's now in the form y minus y1 equals n times x minus x1. So I'm going to get y minus 2 cosh t, capital T, is equal to m, which is this thing, so that's sine of t, divided by the cosh of 2t into x minus the sine of 2t. All right, it's not quite in the form that the question asked, because it wants it in the form ax plus b, where a and b are functions of t. So I'm just going to make this look a bit neater and conclude that y is going to be sine t on cosh t times x. Sorry, cosh 2t on x. So that's going to be a, the gradient. And then my constant, that's going to be negative here, so I'm going to bring this one across first, so plus 2 cosh t. And then the sine t divided by the cos t is going to give me a tan t. It's negative. So I'm going to end up with sine t tan 2t. Okay. And this here is the b. And that is it. That's the equation of the tangent at some general point t. Thanks very much for watching. I hope you have learnt lots. If you still have any questions, just drop them in the comments and I'll get back to you.